Bismillahirrahmanirrahim. Assalamu alaikum, dear students. How are you? This is going to be the part 2 of my yesterday's lecture. Yesterday we discussed about the real numbers, how the real numbers can be converted into binary. Then we discussed about fixed point and floating point representation. I'm sure you have practiced through your worksheet to fortify your concepts. And I'm sure that you have picked on one little fact that if we increase the numbers for the mantissa, we would have better precision for a value. And if we would increase the range of, increase the number of bits in exponent, we will have bigger range of values that we can represent. So increasing the mantissa would increase accuracy, and increasing the exponent would increase the possible range of the value. In today's lesson, we would like to see how many bits we would want to use for mantissa and how many bits we would like to use for exponent. Now, why we need to settle this? Because there can be infinite representation of a value in a floating point format. For example, let's look at this table from a book. It has seemingly three different values, three different representations, but actually they are not different. Let's go through them one by one and convert them into our normal representation, the binary representation, to see if they are different or the same. Now, the first one is 0, which is the sign bit here. And then 001, and then you have 4 in your exponent. This would evaluate to 4. And what I need to do now is I need to convert that. So here exponent is 4, that means I will have to move my binary point 4 positions. Now when I'm going to move it, actually it exists over here right now. When I'm going to move it, 1, 2, 3, and so I have to add another 0 over here to complete my 4 shifts. So that leaves me with 0010, which is equal to 2. For the second row of my table from the previous slide, the exponent over here is 3, which means I have to make 3 shifts. Remember from the yesterday's lecture, exponent is only telling us about where the binary point is going to be. So when I do the 3 shifts, 1, 2, and 3, I would have 010, which is again 2. And for the third and final row of my table, here the exponent is only 2. That makes us move the binary point 2 places only, which would be here, and that is again 2. Now there are 3 different ways to represent 2, and if you just keep playing with your exponent by increasing the number of bits, you're trying different exponents, you can make an infinite number of representation of this 2. But we know that computer cannot use formats like that. Computer has to have a unified, definite formula to represent the values. And we would see one more case and then we would get to that definite and unified way of representation. Let's consider another table, and again this have floating point representation of some number. Let's convert it back. By converting it back, your revision of yesterday's lecture is also being done. So this is my first row, and here exponent is 4, and now you know that I have to move the binary point 4 positions, and this sign bit is also telling you that this value is actually negative. So by moving 4 positions, the point was here 1, 2, 3, and an extra 0, this 0, to make the 4 shifts complete, and it is done. But since the sign bit is 1, we would have to take a 2's complement of this value. So taking 2's complement, it would give us a negative 4. The minus sign is there because the MSB was 1, the value was negative. And moving ahead with the second representation, which is 1100, and for the exponent it has 0011. Exponent is 3, and making 3 shifts over here, 1, 2, 3, the binary point is going to be from here to it is going to be shifted here, and again the MSB is 1, take the 2's complement, the value would be negative 4. The same thing. And again, for the third row, the exponent here is 2, and to actually remove the exponent, we would shift the value 2 places, shift the binary point 2 places, which would leave me with 100. And as the MSB is 1, we would take the complement again, and it would give us a negative 4. Now, with these two examples, we have seen that there are multiple ways of representing a value into floating point format. And this actually makes us want to normalize values. Now, this normalization has nothing to do with the normalization that we studied in the chapter 10 of the AS, the database one. That normalization is completely different from this one. Now, we have established that there are multiple ways, and all of them are accurate, but our computer is not able to use things in this way. It is unable to use things in a uh, way that depends mostly on common sense rather than a definite logic. So that means that we have to actually put a number into normalized representation. We need to write a number in a way that it is normalized. Now, what do I mean by that? That for a positive number, we would not just randomly place a binary point anywhere in the value. We would find the place where the first pair of alternating bits 0 and 1 comes up, and this is where we are going to place a binary point. For a negative value, we would again look for the pair of alternating bits, but in case of the negative value, the alternating bits would be 1 and 0. So we would not just randomly place the point anywhere in the value, but we would find where the values have their number pair of alternating bits, the opposite bits, and only there we would place the binary point. Now, if I would just take you back a little and show you those representations, based on the logic of that I just told you, this would not be normalized. The cross doesn't mean it is wrong. I'm just telling you that it is not a normalized value because it does not have alternating bits in the start. It has identical bits, the same bits in the start. Same goes for this value. It is also not normalized. But this value, this representation of true, this representation of 2 is actually normalized because it is starting from 0 and 1. So this would be the method that we are going to follow. We are going to store the numbers in a normalized format in our computer. So the computer actually knows which representation of a denary value to be used as a standard. That would be the normalized form. Moving ahead, this was the table for -4 that we used. And again, it has same pair of bits in the start. This also has the same pair of bits in the start. But this representation have alternating bits in the start. So that means this one is in normalized form. And this is the one our computer is going to use in order to store a floating point number. Floating point numbers, floating point values are stored in their normalized forms. And the principle, the formula to make the normalized representation is that we place the binary point in the value where the first pair of alternating bits is located. Let's try and understand this with examples. Now we know that why we need to normalize, because we cannot have multiple representation of a same value. It will just confuse our programs. It will just cause errors in our programs. How we normalize? We actually place the binary point in the first pair of alternating bits. Alternating bits means 0, 1 for the positive and 1, 0 for the negative. Now, for example, I have 5.75 and I'm using 8 bits for integer and 8 bits for fraction. I'm sure you have gone through yesterday's lecture and uh, you have brushed up on your skills of converting fraction into binary. It is very simple. The representation would be 101.11. The extra zeros are there are just to complete the 8 bits standard of representation. Now what I'm going to do, I'm going to use a floating point representation, and in that I'm going to use 10 bits for mantissa and 6 bits for exponent. Now, in an unnormalized way, what I did, I just picked the point here and 1, 2, 3, 4, sorry, 5, 6, and 7. I made 7 shifts, and so the value of my exponent would be 7. This triple one is 7. It is stored in 6 bits. And this is my mantissa. The first 10 bits of the value are my mantissa. So, but this is not in normalized. This is unnormalized form. Remember that exponent is not playing any part in the magnitude of the value. Exponent is just telling us where the point is going to be, where the binary point is going to be. Now to write this in a normalized form, what we're going to do is that we are going to just shift our binary point where the first pair of alternating bits is located. Now from the left you can see that first pair of alternating bit is this 0 and 1. Since the value is positive, so I'm going to actually have to look for my 0 and 1. Now I only had to make 3 shifts. So the value of my exponent is going to be 3, and this is going to be my normalized form. How I can recognize this? Because the normalized representation of floating point number will have the pair of opposite bits in the start. I cannot stress this enough. So let's go through another example. That is negative 8.75. After doing the conversion, this is going to be my result. And since the value is negative, I have to take the 2's complement of the value, and this is the 2's complement of the value is going to be. Some students make the mistake of taking the 2's complement of only the integer part. Don't do that. The whole thing, this negative, this minus sign is applied to this value altogether. So we would take the complement all the way. And after taking 2's complement, we have written the value in the fixed point representation. From yesterday's lecture, you know that this representation is fixed point because the place of the binary point is fixed. Now, using the unnormalized form, what I actually would have done is I'm shifting the binary point to 1, 2, 3, 4, 5, 6, and 7. 7 places. So the value of my exponent, again I'm using the same format that I used in previous example, 10-bit mantissa and 6-bit exponent. So the value of my exponent is 7 since I have made 7 jumps, and the first 10 bits of my value have become my mantissa. Now you can see what I meant when I said if I have less number of bits for mantissa, so the accuracy of my value would be compromised. For example, if I had only 8 bits for mantissa here, so I was able to represent only this much value. So these 2 bits would have been gone, and the accuracy of my value would have been compromised. This is what I meant, what I said in the start, that increasing the bits in mantissa, increasing the length of mantissa actually gives you a greater accuracy of your value, and increasing the exponent gives you a greater range of your value. Now this is your unnormalized form. To get to the normalized form, I have to look for the first pair of alternating bits. So the first pair of alternating bits is this one. From the left is this one. So I'm going to actually shift it 1, 2, 3, and 4 decimal places, I think. So my exponent is going to become 4. So as you can see that my exponent is 4. The first 10 bits of my value are in my mantissa, and it is in normalized representation because it is starting from 1, 0. I hope you're able to get all that. It's a bit tricky, but not a very difficult concept. we use normalization to find a standard format to store our floating point values. Now, concluding this, I would suggest that you go through all this material starting from page number 253 of your books. And this is the interconversion of the representation. We have done that in yesterday's lecture and today as well, how we move through uh, floating point to fixed point or fixed point to floating point. It should be very clear to you now. There are some pointers for you. And in the last topic of study would be the problems with floating point numbers. And that is going to conclude our lecture for today. And plus the topic number 1, the chapter 16 is now complete, alhamdulillah. You should have gone through the worksheets up till now and do a lot of practice of the exam style questions. If you have any query, feel free to contact me. Stay safe. Allah Hafiz.